Welcome to another episode of learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held on February 28, 2025. In this video, we discuss the solution of a problem from the section Linear Algebra, and the problem is related to the diagonalizable matrices. This question is placed in part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 704156. This question is suitable for all these examinations. Right. The given question is, let A be a 3 by 3 matrix whose first row is 0, 0, 1, second row 1, 0, 0, the third row 0, 1, 0, and capital B is the 4 by 4 matrix, this 4 by 4 matrix. Which of the following statements are true? We are given four options. Option 1, both A and B diagonalizable over R. And all the options talks about the diagonalizability of A and B over R and over C and their combinations and so on and so forth. Right. These are the four options given to us. Right. Let's now discuss the solution of the problem in detail. Right. To talk about the diagonalizability of the matrix capital A over R or over C, we need to find out the eigenvalues of the matrix A. So for that, we first find the characteristic equation of A is given by determinant of A minus lambda I is equal to 0. This implies the determinant of, take A and from the main diagonal elements subtract lambda. So then you will get the determinant of 0 minus lambda, 0, 1, second row, 1, 0 minus lambda, 0, third row, 0, 1, 0 minus lambda. Take the determinant is equal to 0, expand through its first row and simplify. We will get lambda cube minus 1 is equal to 0. That will imply lambda cube is equal to 1. They are the cube roots of unity. The three cube roots of unity are lambda is equal to 1 omega omega square. Note down, omega square are complex cube roots of unity. Right. So, what are the eigenvalues of lambda? They are not all real. So, the eigenvalues of A are 1 omega square, which are distinct complex numbers. Right. So therefore, A is diagonalizable over C because they are coming from the complex plane and they are distinct. It is diagonalizable over C, but not over R. So we got one of the options true. Option 2, A is diagonalizable over C, but not over R. That is, the option 2 is true. We continue the discussion for the further options in the next slide. Right, that's what we have done so far. Note that this 4 by 4 matrix capital B can be seen as a block diagonal matrix. How? This is one line, you draw a line here and then line here. So this is your A. This is your A, 0, 0, 1. So this is B is equal to A, 0, 0, 1. Right. So the eigenvalues of B are just the eigenvalues of A along with an additional 1 from the bottom right corner, that is a 1 by 1 matrix. From that the eigenvalue we get is 1. From A we get 1 omega square, and from here another 1. Therefore 1 is for B, the eigenvalues are 1 is repeated twice, omega square. And again what we see is not all eigenvalues are real, 2 of them are complex, and so B is not diagonalizable over R. B is not diagonalizable over R. Let's look at our options. So what we get is option 1 is not true. Both A and B are not diagonalizable over R. So A is not diagonalizable over R, B is not diagonalizable over R. Therefore option 1, both A and B are diagonalizable, it is given, but we got not diagonalizable. So option 1 is not true. So 1 and 2 we have discarded. Now our question is B diagonalizable over C? We cannot straight away say B is diagonalizable over C because 1 is repeated twice. So for that we see the algebraic multiplicity of 1 is 2, and if the geometric multiplicity of 1 is also 2, then it is diagonalizable. Now algebraic multiplicity of the eigenvalue 1 is 2 because it is repeated twice. Now the geometric multiplicity of 1 is equal to 4 times the rank of B minus lambda I, where lambda is equal to 1. This is the nullity. 4 minus this is nullity. That is 4 minus rank of B minus I. Lambda is equal to 1, B minus I. So what is the rank of B minus I? So we take B minus I, this is B here. Minus I means along the diagonal minus 1, minus 1, minus 1, 1 minus 1, 0. This is 0. This is 0. B minus I. So what you do is you write R4, R3 is R3 plus R2 plus R1. If you add and write at the third row, this is again 0, 0, 0, 0. So you get, now the first 2 rows are linearly independent. It's very easy to see. So the rank of B minus I is 2. So come back here. So the geometric multiplicity of 1 is equal to 4 minus rank of B minus I, that is equal to 4 minus 2, that is 2, that is equal to algebraic multiplicity. Thus the algebraic multiplicity of 1 is same as the geometric multiplicity, and they are repeated only once, therefore their algebraic multiplicity and geometric multiplicity coincides. Thus the algebraic multiplicity of every eigenvalue is equal to the geometric multiplicity of that eigenvalue, and hence it is diagonalizable over C. Right. Now option 4 is not true. Why it is not true? The option 4 says neither A nor B is diagonalizable over C, but A is diagonalizable over C, B is diagonalizable over C. Therefore option 4 is not true. Now look at option 3. Neither A nor B is diagonalizable over R. Correct. But both A and B are diagonalizable over R, over C. Yes, this is true. So thus the answer to this question is options 2, which we have already seen, and option 3. That is the detailed discussion of the solution of this problem from the section Linear Algebra, which is related to diagonalizable matrices. Right. I am sure that you understood the solution of this problem. Thank you for watching this video. Now I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Yes, I am going to meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.